A very good day to everyone. Today, myself, Dashan Murali, CE240133, followed by my friend Muhammad Afiq Ehsan bin Muhammad Sahuri, CE240217. We will be presenting our project presentation for Signal and System. We are from Group 2, Section 4. Okay, for calculation, for task 1, we're going to search for Fourier series coefficient. So for number 1 is n equals to 0, so it's obviously it's a DC, so type of DC signal. So what we'll do is x1 x naught equals to 0.5 sine 0 0, therefore we get answer of 0.5. For n equals to 1, we get a 0.5 into sine pi over sine pi into zero point 0.5 over zero point 0.5 into pi, so we get zero point 0.5 times 1 over 2 pi, so the answer will be 1 over pi. So since it's an even signal, odd signal, therefore the even signal for 2 4 6 will be 0. So we straight away jump into n equals to 3. So upon n equals to 3, we get answer of 1 over 3 pi, and followed by n equals to 5, you get a 1 over 5 pi. So the signal is progressing in odd signal, and in the form of 1 over pi, 1 over 3 pi, 1 over 5 pi, 1 over 7 pi, and so on. But also we need to here notice here is there's also a negative in a 1 over 3 pi, and a 1 over 7 pi is negative. So therefore the signal is changing from a positive negative positive negative positive once again negative, if moving in that kind of row.
Assalamualaikum everyone. So just now my friend Dakshan already explained how we get the magnitude xn. So we can calculate the increase of n. So the magnitude is decreased. So we continue to get the low pass filter LPF. So our equation is magnitude HF equal to 1 over square root 1 plus F over FC square. So we just include the value into the equation. First of all, h not equal to 1 over square root 1 plus 0 equal to 1. And then when uh, when the n is 1, frequency 100k hertz equal to 1, we got the answer 0.9464. We continue with n equal to 3 with frequency 360 kHz, and we got the answer 0.822. And last but not least, when the n equal to 5 with 600 kilohertz, and we got the answer 0.6247. Thank you.
So for next xn, we need to multiply into h n f naught. So we make a table first, okay, for the Fourier series coefficient we found the first three. So 1 over pi, 1 over 3 pi, 1 over 5 pi, and we multiply it into the hn we found earlier, presented by my friend. So you'll get 1 0.94 0.822 0.6247. So once we multiply, we get x naught in a filtered version. So upon getting it, this is our answer, which is 0.5, 0.314 not, 0.0572, 0.398. Okay, that's for task 4. For next task 5, we get to that duty cycle in the effect. So for x1 equals to, since it's 10%, okay, so it's 0 0.1. So we change it into 0 0.1 into sine 1 times 0 0.1 over 0 0.1 pi. Okay, the same thing goes to x3 and x5. So we get answer of 0.094, 0.0935, 0.837 respectively. Okay, for the coding, okay, we have I've done a three parts, task one, two, and three. So let me explain the coding. So it's given from the question that our fundamental frequency or FO is 120 kilohertz. So for kilohertz, we are using E3 in behind, that followed by for cutoff frequency 750 kilohertz, and for period or tau, we use for period t, we use the formula is 1 over f. So that's the thing I included here using the formula. And for tau, we use since the pulse width is duty cycle is 50%, so we use the 0.5 TO. TO is time. So how we get time? Once again, we derive from this formula. Okay, for task one, Fourier series analysis, we need to determine the number of harmonics. So we get a 5, 10, and 20. So 20 number of harmonics. So and also we get time. So 3 negative 3 t naught. Okay, so we get from 1 over frequency. Then so a positive 3 to into t naught, and followed by y into 1000. So the graph we need to let know what is the type of task 1 domain analysis. Okay, so this is the formula for xn equals to tau or t naught into sinc n tau over t naught. So n is a number of harmonics we would search. Okay, so after we reconstruct the signal, and also we plot a time domain signal, so it will change into task one signal deconstruction with n plus minus harmonics. Okay, so we will run the signal, and at the end of this coding session, okay, followed by task 2. Okay, we get research for 20 number of harmonics frequency domain analysis. So for this, xn equals to tau over t naught into sync n tau over t naught. So it just used to frequency domain. So we use magnetic spectrum, and to convert to kilohertz is here is n f naught over 1 kilohertz. Okay. So the axis will be x will be frequency in kilohertz, and y equals to the magnitude. So modulus xn. So lastly is low pass filter design analysis. So we know that our R is we know the R. So for task 3 we use RC filter parameter. So it's given C is 1 nanofarad. So we use R. We determine the R using the formula 1 over 2 pi FC1 nanofarad. Okay. So upon the calculation, we can calculate the frequency response. So F line space 0 to 2 times FC, and so the frequency range is 1000. So H is equal to 1 square root 1 plus F over FC square. So we'll search, we'll make it as a filtered graph. So task 3 filter characteristic will be should be popping out. So we need to determine in dB. So what we will do is we change the signal into 20 log base 10 to H. Okay, so we need to convert it to decibels since we want to know the low pass filter. Okay, so x axis will be kilohertz in frequency, y axis will be gain in dB. So it will pop out a graph with task 3 filter frequency response in linear scale. Okay, and also in a while we will see this result into 5 harmonics. Okay, is 2.5 to negative 2.5. Okay, so we can see the signal over here. We could know how much is it, followed by 10 harmonics. Okay, so we could move, we could see how much the graph has been traveled, and followed by plus minus 20 harmonics. Okay, so this is for task 1, and for task 2 here we could see the magnitude spectrum. Okay, magnitude spectrum. So we could see in 0 it's the high because of 0.5. Okay, since the formula for Fourier series it's known as integration tau to 0 and xt. So since our xt is equals to 1, and also our tau into t is has a difference of 0.5, therefore the result over here is correct. Okay, so it's traveling in the same level for all of the signals. So for task 3 for filter response, okay, we could see it's a low pass filter in a design. Okay, this in magnitude it's also in showing in a dB. Okay, followed by in a linear scale also it's showing from in a design which have been stated in the pre-lab or pre-projects, and also in the in the project sheet. Therefore, the coding has been tallied with the calculation, and over for task 4 and 4, 5, and 6, and so on will be presented by my group mate. Thank you.
In conclusion, this project demonstrates how Fourier series can be used to analyze and reconstruct a square wave signal and show the importance of higher harmony in shaping its waveform. By designing a simulating an RC low-pass filter, we observe how it effectively reduces this high frequency component, resulting in a smoother signal. The study also highlighted how varying the filter's cutoff frequency and the signal duty cycle affect the filter output. Overall, this project helped us better understand signal behavior in both time and frequency domain and the practical role of filters in signal processing.
So that's all from us. Thank you very much for listening. Hopefully, everyone get a wideful for understanding from our pre-project presentation. Thank you.